Let's start from square one. We will define an arena of space as a dimensionless unit, 1 square. That is a square with 4 equal sides of length 1, with an area of 1 and a perimeter of 4. Let's divide the square into 4 equal quadrants and plot 4 significant points. We will connect point A to point N as well as point A to point E. This will create 2 angles defined as quadrian angles. The length from point A to either point N or E is defined as Q, the quadrian ratio. Both the quadrian ratio and angles are fundamental constants. They are the only angles that will perfectly bisect any sized circle into quadrants from the origin of point A. The ratio sits exactly in between the golden ratio and its reciprocal, with the value of QO plus or minus 1/2. For this reason, the quadrian ratio is sometimes referred to as the golden seed. If we look closer at the length of point A to E plus point E to B, we in fact find the golden ratio itself. Adding the length point A to B to these lengths creates a triangle with a perimeter of the golden ratio squared. There are 2 of these golden ratio triangles in our arena on either side of the quadrian angles. The golden ratio has a number of unique properties. It is the only number that, when squared, equals itself exactly plus 1. It can be related to how things grow in the natural world. Now things get even more interesting. If we connect point N to point B, something fascinating happens in between the quadrian angles. We find a right-angled triangle. This is not just any 90-degree triangle. The ratio of this triangle is the exact ratio of the Pythagorean 3-4-5 triple. The smallest triple to which the hypotenuse is a whole number. This property is unique to this ratio. This now connects the arena intrinsically to the Pythagoras theorem and highlights a third significant quadrian angle, what is referred to as the Quadrian view, from the origin point of A. Throughout history, many have used geometry to get a better understanding of our world. The Pythagoras theorem is the best example of that. It has been known for more than 4,000 years. The Pythagorean theorem is arguably one of the most important mathematical and geometric truths. Everything we understand about geometry, and therefore math, physics, and science, stems from this fundamental fact. It is a significant foundational absolute, repeatable, precise, and exact. Here, not surprisingly, we have found it literally at the heart of our basic arena construction. The connections and coherence of these constants and geometric principles of this simple arena are striking already, but we are just getting started. This is a very basic construction, but it contains so much more information than one would expect. Suppose we think of the 2 quadrian angles as paths, 2 possible paths in our arena. We have 2 particles which both move linearly at the exact same constant speed. They also rotate and change their headings or vector at the exact same constant speed. Each particle follows their respective paths and travels the same distance in our arena. When we run this model, we find that while both particles move at the same speed and travel the same distance, one particle arrives slightly sooner in time than the other. Why? How is that even possible? This is a very real result and is not a trick. The logic and math behind it is actually simple and easy to understand. It is not immediately obvious that one particle effectively spends more time rotating than the other when changing its heading. This means that while both paths are identical in terms of the distance traveled in the arena, when accounting for the degrees traveled in rotation by each particle, the paths are no longer identical, almost as if time and angles themselves are interconnected somehow. Let's examine these 2 paths in more detail to see what else we can find. Each particle travels 8 equal legs of distance in the arena-changing direction at 7 different points. These are the points of rotation. Each point has a kind of potential angle, which when summed is different for each path. This potential, in part, is where things go from interesting to remarkable. Through this simple function, called the Quadrian path equation, if we set n to the value of the northern path's angular potential, we find a stunning result. If you like coincidences, the result is the precise latitude for the Great Pyramid of Giza, which just happens to share its digits with a little something in physics known as the speed of light. What is really going on here? The speed of light has been measured to an incredible degree of accuracy. It was defined by the International Committee for Weights and Measures as 299,792,458 meters per second. There has never been a geometric proof for the speed of light, nor any explanation as to why it is the precise speed that it is. Just that it is a constant for all frames of reference. Yet here, it just falls out of our simple geometric arena, and this is just the tip of the iceberg. Looking back at our Quadrian path equation, we find another curiosity. If we simply move one value in the formula, we actually get what appears to be the speed of light at scale. Not in the way you would expect, either. This value is technically even closer to the most accurate measurement of the speed of light than what is currently defined. Let's also not forget that we have two different paths in our arena. What about the second path? Using the angular potential of the eastern path as a value for n, we find a number slightly higher than the speed of light. Could it be that there are two speeds of light? If not, what could the other speed be? This is very intriguing. What is this Quadrian path equation exactly, and how was it derived? Let's take a look. What else can we learn about this arena? Let's break down our Quadrian arena and look at some of its other properties and significant numbers. The number 2, 5, and the square root of 5 are the key to the Quadrian and golden ratios. Here again, we find these same numbers at work in the Quadrian path and speed equations as a value being subtracted from a term derived from various properties under different spatial contexts. If we inscribe a hexagon into our space to fill the circle and look very closely, we find something that is usually a common mistake. This is either something that is not noticed, mentioned, or even forced when it comes to hexagons and connecting all 6 points to the circle. This is actually wrong. A true hexagon will only touch the circle it is inscribed in at 2 points. This is along the equator if you think in terms of hemispheres. This is why two of our initial points are called N and E, which stand for north and east. There is a similar fact about circles themselves. For any number of points making up any sized circle, the points along the equator connect differently than they do at the poles. There are debates about points and whether they take up space or not. This does not matter either way. There are intrinsic Quadrian differences with how points connect forming any sized circle. This is why bubbles always connect at 120 degrees, regardless of their size. The geometry of this is fascinating. What else can we learn? Are there any other constants connected to the Quadrian ratio and this arena? If we rotate our Pythagorean 3, 4, 5 triple from the origin point of A as the axis, so that it is flush with the bottom of our arena, we find yet another curiosity. The distance from the right side of the triangle is almost exactly 1/10, but ever so slightly over. Upon closer inspection, another clue emerges. This difference seems to be related to the natural logarithm. Could it possibly be? Euler's E is a well-known constant. It is not geometric and purely calculus. It is used to calculate rate of change or growth, often in financial markets, when dealing with compound interest. It is referred to as the natural language of calculus because of its unique property when plotting the function e to the x. It is the only number that has the same value, gradient, and area regardless of where it lands on the plot. It turns out we can also find e in our Quadrian arena. If we take our numbers 13 and 30 again, this time as a fraction, and subtracted from 5. Then multiply that by the golden ratio. and look at the square root, you will in fact find a number that is incredibly close to Euler's E. What's more, it is slightly less, which could mean that the infinite series used to calculate Euler's E could be converging to this value in much the same way the Fibonacci sequence converges to the golden ratio. Could this be a geometric link? What about pi? We find pi everywhere, not just in circles. We find it in probability theory, the swings of a pendulum, the length of a river, and many other places that have nothing to do with circles, at least on the surface. The concept of pi has been used for more than 3,500 years, dating back to ancient civilizations. Early estimates of pi were developed by the Egyptians and Babylonians around 1900 to 1600 BCE, with approximations like 3.125 and 3.16. In ancient Greece, Archimedes, circa 250 BCE, significantly improved these estimates by using geometric methods to calculate pi more accurately. The symbol pi was introduced in 1706 by William Jones and popularized by mathematician Euler in the 18th century. Over time, through more than 120 generations, methods for calculating pi have evolved. Initially, geometric approaches were used, but by the 17th century, mathematicians like John Wallis and Isaac Newton developed infinite series to compute pi with greater precision. In modern times, computers have vastly extended the known decimal places of pi, reaching trillions of digits. This very much makes it seem like a given that we understand pi, doesn't it? Well, when we measure and find pi in the natural world, what do we see? It always seems to be an approximation. If we are right about pi, should we not see the exact value of pi turn up more often? Especially when dealing with circles and spheres. That's not actually what we observe. We get different measurements or approximations of pi everywhere. Why? What's really going on? Does our model tell us anything about pi outside of the circle? In the year 1920, Srinivasa Ramanujan discovered that e to the power of pi multiplied by the square root of 163 produced a value incredibly close to a whole number. This is completely unexpected for what is thought to be three irrational numbers. This is called the Ramanujan constant. In the context of our model, if we take our quadrian e and the square root of 163, can we derive and calculate pi? What happens if instead we treat the Ramanujan constant as a whole number and use that to derive pi from the natural logarithm? Doing this, we are able to easily calculate pi to 32 decimal places according to the accepted value of pi. While this was the expected result, for the most part, what was not expected is the fact that if you take the large whole number, reverse the order as a decimal, and divide that into 1, you will get a number that is extremely close to the square root of 5. It truly is mind-blowing.